The virus that causes COVID-19 is mainly transmitted through droplets generated when an infected person coughs, sneezes, or exhales. A person can be infected by breathing in the virus if you are near someone who has COVID-19 or by touching a contaminated surface without protection. We can do things to protect ourselves and others from COVID-19, like wearing a mask, avoiding crowds, and maintaining distance from others. Probability is very useful in determining and understanding real life situations and problems of everyday living. For example, we can estimate the probability of an infected person infecting another person by coughing in the context of COVID-19. Probability has numerous applications in real life. It is widely used in areas like weather forecasting. A probability forecast it will rain or any probable weather conditions for a particular hour, day, or week. In games, poker, gambling, or video games use probability to know how likely a person has chances to win. In medical decisions, when doctors advise patients to undergo surgery, probability is used to know the success rate of the operation. Hello everyone, I am Sir Jan. Welcome to my video lesson in math. In this video, we are going to learn about the probability of the union of two events. Our objective is to find the probability of the union of two events, whether mutually exclusive or not. Recall that in tossing a coin, the probability a head will appear is 1 over 2. And the probability of rolling a 3 on a die is 1 over 6. Now, what is the probability of drawing the ace of hearts from a deck of cards? Yep, you're right. It's 1 over 52. The given problems involve simple events. A simple event is an event where one experiment happens at a time and it will be having a single outcome. Remember that an event is a set of possible outcomes resulting from a particular experiment. A sample space, on the other hand, is a collection of all possible outcomes of a random experiment. An event associated with a random experiment is a subset of the sample space. Now, what about getting the probability of rolling an even number less than 5 on a die? Looking at a die, the even numbers are 2, 4, and 6. And the numbers less than 5 are 1, 2, 3, and 4. Therefore, the answer is 2 over 6, which is equal to 1 over 3. Let's have another. What is the probability of drawing a red ace from a deck of cards? Answer: 2 over 52, which is equal to 1 over 26. The problems we just answered involve compound events. A compound event is more complex than a single event, for it involves the probability of more than one outcome. Another way to view compound event is as a combination of two or more simple events. In tossing a coin, we get one outcome that is a head or a tail. The events cannot occur simultaneously since the events have no elements in common. Events are said to be mutually exclusive if the intersection of a given set A and a given set B is an empty set. Otherwise, they are not mutually exclusive. How do you find the number of outcomes in a union of events? If you find the sum of the number of outcomes in event A and the number of outcomes in event B, you will have counted the number of outcomes that are in both event A and event B outcomes twice. In the given illustration, the outcome is equal to 1, 2, 3, 4, and 6. 2 and 4 is not written twice. Therefore, in order to correctly count the number of outcomes in the union of two events, you must count the number of outcomes in each event separately and subtract the number of outcomes shared by both events. So these are not counted twice. Consider the two sets. Event A is a set of positive odd integers less than 9, and event B is a set of positive even integers less than 8. The two events are sets that have no common elements. Notice that there is no overlapping. Even if we try to overlap the two circles, they do not share the same outcomes. The outcomes here is the set 1, 2, 3, 4, 5, 6, and 7. And the number of outcomes is 7. So how do we calculate the probability of these kinds of events? We said earlier that if event A and event B are in the same sample space, then the probability of A union B is given by the probability of A union B equals the probability of A plus the probability of B minus the probability of the intersection of A and B. But since the probability of the intersection of A and B is an empty set, then the probability of the union of A and B is equal to the probability of A plus the probability of B. Let us observe the two sets of events. Look at the illustrations. In mutually exclusive events, we can see that there are no elements in common to both events. While in not mutually exclusive events, we have the King of Hearts being common to event A and event B. Let's have example 1. What is the probability of drawing a 7 or a face card in a standard deck of cards? First, we let S be equal to the 7 of clubs, 7 of spades, 7 of hearts, and 7 of diamonds. And let F be equal to the Jack of clubs, Jack of spades, Jack of hearts, Jack of diamonds, Queen of clubs, Queen of spades, Queen of hearts, Queen of diamonds, King of clubs, King of spades, King of hearts, and King of diamonds. We must remember that there are 52 outcomes in a standard deck of cards. Now, are the events S and F mutually exclusive? In the given example, it is clear that there is no common element between A and B. So to get the probability of a 7 or a face card is to get the individual probability of 7 and face card, then you add them. So we have the probability of 7 is equal to 4 over 52. The probability of face card is equal to 12 over 52. So therefore, the probability of 7 or a face card is equal to 4 over 52 plus 12 over 52, which is equal to 16 over 52. In lowest term is equal to 4 over 13. From the given data, we can check whether our solution is correct or not. Let us have the probability of S union F is equal to the probability of S plus the probability of F. We have 4 over 13. Is it equal to 4 over 52 plus 12 over 52? We have 4 over 13. Is it equal to 16 over 52? 16 over 52 is equal to 4 over 13 in simplest form. And since both sides of the equations are equal, therefore, we can say that S and F, or the event of drawing a 7 and the event of drawing a face card, are mutually exclusive events. Now let's move to example number 2. A card is drawn from a standard deck of cards. What is the probability of drawing a heart or an 8? We must remember that there are 52 possible outcomes in a standard deck of cards. So let H be equal to the event of drawing a heart, and H therefore is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King of hearts. And we let E be the event of drawing an 8, and E is equal to 8 of clubs, 8 of spades, 8 of hearts, 8 of diamonds. Now, are the events H and E mutually exclusive or not? In this example, there is a common element in the two events. So therefore, we have the probability of H or E is equal to the probability of H plus the probability of E minus the probability of the intersection of H and E. So first we get the probability of H. So we have 13 over 52. And then we have the probability of E. It is equal to 4 over 52. And the probability of the intersection of H and E. It is equal to 1 over 52. Now by substitution, we have now the probability of the union of H and E is equal to 13 over 52 plus 4 over 52 minus 1 over 52. Simplifying, we have 16 over 52, which is equal to 4 over 13. Clearly, there is an element common to H and E. It's 8 of hearts. So let us check. Is the probability of H or E equal to the probability of H plus the probability of E? We have the probability of H or E is equal to the probability of H plus the probability of E. By substitution, we have 16 over 52. Is it equal to 13 over 52 plus 4 over 52? So we have 16 over 52. Is it equal to 17 over 52? No, it is not. So therefore, H and E, or the event of drawing a heart and the event of drawing an 8, are not mutually exclusive events. Using one of the given illustrations earlier, please do observe the formulas that will be used for the union of two events with mutually exclusive and not mutually exclusive events. So for events that are mutually exclusive, we have the probability of A union B is equal to the probability of A plus the probability of B minus the probability of the intersection of A and B. And in case we have mutually exclusive events where the intersection of A and B is equal to an empty set, the probability of A union B is equal to the probability of A plus the probability of B. Now let us check your understanding by answering the following problems. Number 1. In a deck of cards, we have 13 club cards and 12 face cards. There are 3 common elements in the given problem: Jack, Queen, King of clubs. Therefore, the probability of getting a club or getting a face card is 13 over 52 plus 12 over 52 minus 3 over 52, which is equal to 22 over 52, and when simplified is 11 over 26. The event of getting a club and the event of getting a face card are not mutually exclusive events, since there are common elements. Number 2. Since we have 3 red balls, 5 blue balls, and 4 yellow balls, the sample space is equal to 12. Therefore, the probability of the union of getting a red or a blue ball is equal to 3 over 12 plus 5 over 12. Since there's no common element, we now have 8 over 12, and when simplified is 2 over 3. The event of getting a red ball and the event of getting a blue ball are mutually exclusive events. I will leave you with some problems to answer and practice. And that will be all for now. Thank you.